Okay, thank you very much for your cooperations and understandings. Now, Dr. Bruce A. Linquist, University of California, Davis in the United States of America, will give you the keynote speech. And Dr. Keiichi Hayashi will be the moderator of the session. Please give a round of applause to Dr. Hayashi.
Good morning, everyone. My name is Hayashi, Program Director of JIRCAS, Japan International Research Center for Agricultural Sciences. I'm pleased to be chair of this session. And then this keynote speech session. And then our guest, Prof. Bruce Linquist from UC Davis. And let me briefly introduce him. He has obtained his PhD in agriculture ecology at University of California in 1995. And after that, he worked at IRRI, International Rice Research Institute, in Los Banos for since 1997 to 2005, 8 years. And then he covers very broad areas in research, including crop systems, nutrient carbon cycling, and greenhouse gas emissions, varietal adaptation, water use efficiency, water quality, crop growth development. So he talks about today's his speech. His talk is, he touched upon mitigating green gas emission and heavy metal uptake. So we start hearing his talk. So Bruce, the floor is yours.
So I just used the. Is this gonna? Will this get projected up there? Ah, thank you. Well, thank you very much. I'm very honored to be invited here, and I want to thank the organizers for taking care of everything so wonderfully. And it's a topic I've worked a lot with over many years. I've been working in rice for about 25 years. And this area of research is an area that's of great interest to me. So I'm happy to give a keynote, but I'm also very excited to hear what other speakers have to say and to see more of what's going on in the region. I worked with IRRI for 8 years in Asia. I've been back in the US now for 15 or so years. So it's nice to be back. Oh. Can you hear me okay? How do I? Okay, very briefly, the outline of my talk today, I'm going to cover the first half of my talk going over the problem. I think a lot of this may be very familiar to you, but certainly setting the stage for this symposium. I think it's important. We're going to look at just a little bit on greenhouse gases and heavy metals. And then the last half of my talk, I'm going to be talking about how do we achieve desirable outcomes. I'm very happy with this symposium. It's really focusing on the applied, and that's an area that I've worked a lot in the applied. I'm going to be giving some experience of mine from California, but I'm also going to be kind of wrapping up with just some thoughts on yields and maybe some of the limitations of water management. So very quickly, again, this is, I don't think, new to any of you. As we've just heard from a number of our previous speakers, climate change is there. It's necessitating a reduction in greenhouse gas emissions. When we're talking about agriculture, certainly we're looking at methane, nitrous oxide, CO2. We know that methane, roughly 28 times more potent than CO2. Nitrous oxide, a much more potent gas, over 270 times more potent than CO2. And when we look at, we're going to be talking about global warming potential, we usually consider CO2, the methane, N2O on a CO2 equivalent basis. However, when I talk about GWP, we're not going to really be including CO2. Usually on an annual basis, CO2 balances out. Just very quickly looking at the contribution of agriculture and forestry. to global greenhouse gas emissions. We're looking at about 22% in agriculture. That is not changing that much over the past couple of decades. If we really focus on methane, which is really going to be the heart of what we're talking about in rice, agriculture contributes a fifth to a quarter of global methane emissions. And if we look inside of that, rice and their rice systems are contributing about 15 to 20% of methane emissions. Again, livestock is really the sector that is really putting out much more in terms of methane, but rice is coming in second and contributes a significant amount. Again, with rice, methane is really the big issue. And when we look at gases from other crops, this was a paper I did a number of years, over a decade ago now, but we'll see that N2O is emitted from all crops, but really when you look at rice, it's that methane that really stands out. And because of that, the GWP from rice, of those rice systems, about 3 to 5 times higher than you would typically expect from wheat or maize. N2O is usually very low, but we need to keep it low. When we start using water management as a lever to adjust for methane, N2O can go high. We need to be very careful of that, and that's going to be a theme that I'll be talking about through the course of this time. The next thing, heavy metals. Certainly with the more educated consumers, the press, increasing concerns in terms of heavy metals. Articles such as how poisonous is our rice. I hear it. I work in rice, and people come up to me, is it safe to eat rice? It's becoming a bigger concern for people. Which heavy metals are a concern? I've listed 5 here: arsenic, cadmium, lead, mercury, chromium. 3 of those are carcinogenic. You look at lead, mercury, they both are related to neural behavior and neurotoxicity issues. If you look in the literature, I just did a very quick search of the Web of Science, putting in rice versus the heavy metal. You can see arsenic and cadmium have received by far the most attention. I looked at the program, and I think cadmium and arsenic are to be talked about most in this. But lead and mercury and cadmium are also of concern. And the list is growing. In 2026, EU is going to be adding nickel to rice. There's going to be a limit, a concentration limit placed on nickel. Nickel causes reproductive and development toxicities. So the amount of metals that we need to be concerned with is growing and may continue to get larger. You can see very little information on rice and nickel when I did that same search. So if you look at the heavy metals and the maximum concentrations, this kind of gives a list of what the maximum concentrations are. I want to just draw your attention to a couple things on this list. First is we don't see arsenic, total arsenic. We see inorganic arsenic. A lot of our studies, we look at total arsenic. It's cheap to measure total arsenic. It's expensive to measure inorganic arsenic, but none of the levels call for, none of the guidelines call for a restriction on total arsenic. It's inorganic arsenic. The other thing I want to bring to your attention is critical levels. They vary by grain type. Are we talking paddy rice, brown rice, polished rice? It varies, as you can see through that list. It varies by regulatory agency. We have Codex, which is perhaps the most widely used, but then there's a Chinese National Standard Unit. We have the Commission Regulation EU that just put out the nickel. We got in the US, the US FDA. All have different types of regulations, and the regulations vary by age. So if you look arsenic and lead, you see that some of those are restricted to what's being fed to infants or children. And then you're going to see various, if you look closely through that, differences depending on region. And certainly when we look at toxicity concerns, it's a function of how much rice is in the diet. Certainly here in Asia, it's much greater than the rest of the world, and thus probably a greater concern. There's parts of Asia where you're looking at 200 to almost 300 kilograms of rice consumed per capita. You look at the other locations, Europe, Americas, Africa, I put the highest and lowest countries in each of those, and you can see they're much less than we see here in Asia. So that is another factor affecting, if you're going to be eating a lot of rice, you're going to be a lot more concerned with the quality of that rice. So I want to shift a little bit to what happens when we drain a field. And certainly, I think a lot of you are familiar with this, but methane, it's the end product of organic matter decomposition under anaerobic conditions. When we put in an aerobic event, mid-season drain, AWD, we alter the redox potential. It reduces the methane production within those systems, and hence it reduces the emissions. There's a lot of review papers and stuff, some of which I've been involved in, but generally you're looking at reductions of methane from anywhere from 30 to 75%. And water management is a powerful tool in this. It's a good way to affect it, and how you manage it is important. And again, a lot of papers point out this, and this is just another paper I was involved with, but just how long are those drying periods, how severe are those drying periods, all affect the methane emissions. Clearly, as I've already alluded to, in our quest to reduce methane, we don't want to be increasing N2O. Certainly when we dry and reflood fields, we're going to set off nitrification and denitrification. Both of those reactions can lead to N2O emissions. So they're both very critical. So certainly when there's a high amount of mineral nitrogen in the soil, mineral extractable nitrogen, N2O emissions can be high and override any benefit that we might see from a reduction in methane. Again, nitrous oxide, a much more potent gas. In this graph off to the right there, that's a study I was involved with in Italy. And you can see permanent flood, AWD. The AWD had a much higher GWP simply because of the very high N2O emissions. So 2 take-home messages: we need to always be measuring N2O. When we're doing these water studies, N2O needs to be measured. We need to know that that's not increasing. Secondly, we need to co-manage nitrogen, specifically fertilizer, but we need to know what the nitrogen levels are in those soils and water if we want to keep our N2O low. The effect of draining on heavy metals, it really varies according to the type of metal we're looking at. So this kind of complicates things a little bit. Certainly, when we look at arsenic, mercury, and primarily lead, we see that when we introduce drainage events, there's a reduction in uptake and a reduction in the concentration in the grain. There are some studies that maybe suggest that lead increases a little bit or there's very little effect. But the latter 3, cadmium, chromium, nickel, they all increase when we have a drainage event. So this suggests that win-win scenarios, they're certainly possible if you're looking at those top ones. It becomes greater challenge when we start to think that cadmium may be there or some of these other heavy metals. So it really is important when we're implementing these strategies to understand what's in our soils. Are they contaminated soils? Are they high in various types of metals that we need to be concerned with? And I'm not going to go into a lot on this slide, but I mentioned in the previous slide that it's a challenge. And I just bring up this slide. This is a very recent paper by Zhang et al. That included a colleague of mine at UC Davis. But it just suggests that there are possibilities, even in this case, where they were able to simultaneously reduce arsenic and cadmium with either the use of biochar or calcium, magnesium phosphate. So really understanding some of the biogeochemistry in this case and that basic science is really important for us as agronomists to be able to then potentially apply some of these practices and use some of these things. So I would just suggest very broadly that There are numerous areas to study, number of disciplines that are important as we think about water management and heavy metal toxicity in rice. Certainly, toxicology, more the medical side, but it's important. What are the problem metals? Which species are toxic? Certainly we see that with inorganic arsenic versus organic arsenic. Some of them are worse than others. I guess I'm guessing our audience here fits into one of these latter three categories, either soil biogeochemistry or microbiology. Very important in just understanding these metals are all naturally occurring in soils, and sometimes there's contamination. How these metals behave under changing redox, what happens that affects their speciation, their mobility in the soil, their bioavailability is all important things we need to do. There's a lot of effort, especially looking at the effect of iron plaque on the soil. Is it a barrier? Does it facilitate uptake? It varies, and it's very important things to know and affects what we do in the field. Certainly a large role for plant genetics, plant physiology, uptake, translocation, and remobilization in the plant. What is being taken up? How it's being taken up? Can we affect that? And certainly some species are a lot more mobile than others in the plant. And finally, agronomy, that's kind of where I fit in. How can we take all of that other information and make it work in the field? It gets into issues like the timings of these drains, the amount, the severity, all of which affect emissions and uptake. So I want to just look at some of these things in relationship to a study that one of my postdocs did a couple years ago. It was Daniela Carrillo. She did a machine learning analysis review. I'm not going to go into all the details, but basically comparing AWD versus continuous flood treatments on the effect of cadmium and arsenic in response to a drainage. We know that they behave in opposite ways. So just going to pull out a few things that I think are important. In terms of total and inorganic arsenic, the most important thing that was affecting the uptake of arsenic was the soil water potential. That's how dry the soil was at the end of a drain period. So that was the most important. You can see it in both the top, total arsenic, the bottom, inorganic arsenic. But AWD had a greater effect on total arsenic than it did on inorganic arsenic. And you can see that in the right-hand side where the green arrows, the critical drying point for total arsenic, a 40% reduction at minus 20 kPa. Minus 20 kPa is still a very wet soil. However, to only get a 32% reduction, you had to dry the soil more, and that was down to minus 45 kPa. So a difference in how these two species, the speciation is affected. And I'll get into a little bit more that later. We would like to say that, well, I'm just going to measure total arsenic. And then I'm going to assume a constant ratio between the inorganic arsenic to total arsenic. We would like to assume that the ratio is constant, but it's not. If we look up here, and I'm just going to see if you look up here, this is from Zhao et al. Along this bottom axis is total arsenic. Along this axis here, the y-axis is inorganic arsenic. You can see that in some cases, inorganic arsenic is 100% of the whole arsenic, or all the way down to about 20%. So the ratio varies. It varies by region. You can't assume a given ratio. In the Carrillo et al. Study, we saw something else, that it varies by water management because you have a greater effect on organic arsenic. And so what you see is as you get drier here, as with AWD, soil water potential is more dry. This green line here is the ratio, the percent of inorganic arsenic. You see that it increases as you get drier because you're reducing the organic arsenic more than you are the inorganic arsenic. So really, if we're going to understand this and meet standards, we're going to have to be able to measure inorganic arsenic. Very quickly looking at the impact of drying on cadmium, we also saw that drying was very important. We saw that there was a linear response. With more drying, we get greater uptake, just as we would expect. However, the most important thing for cadmium was the timing of the drying. Cadmium was most taken up when we had early drains during the early reproductive period. That is sometime between PI and booting. And you can see here that when there was a drain during that critical early reproductive period, cadmium uptake was almost double that. So we need to be careful on the timing of the drying. And you're going to see later on that actually that booting stage is probably when we get our greatest reduction in arsenic. So I'm going to shift now into achieving desirable outcomes in the field. And this is kind of a little bit of what we've done in California. And then I'm going to finish it off with some final thoughts. So I know a lot of you are not familiar with California rice. It's very different. I've worked in Asia for 8 years and now in California for about 15 years on rice. And it's a very different system. So I'm going to explain it very bit. It's a water-seeded system. It's a direct-seeded, water-seeded system. This is a field just ready for planting. It's completely flooded, about 10 centimeters of water, and an airplane is going to come across and apply seed to that. So it will stay flooded until about 3 weeks before harvest. So it stays flooded for a very long period of time. We also have very large field sizes, 30 to 50 hectares in size. So it takes a long time to flood a field, some to 3 to 7, 8 days sometimes. It takes similarly a long time to drain a field when you need to. So it's not something that you can do very rapidly. However, we have an ideal climate and irrigation infrastructure for very good water management, for very precise water management. During the growing season, we have no rain. In June, July, August, really no rain to speak of at all. So when we want to dry, we can dry. There's no rain interfering with that. We also have a very good irrigation infrastructure that supplies irrigation to individual fields. So, needed to identify practices that work within the system. Certainly one practice that I'm not going to talk anymore about is shifting to dry seeding. So typically in the left photograph there, we're water seeding. That's a plane flying on. We're in the field broadcasting in a variety trial right there. But shifting to dry seeding where you're planting with like you plant maize, the rice is really aerobic for that first month. We're able to reduce methane emissions by about 60% by that shift. I do not have any information on these systems with regard to heavy metals, and I'm not going to be talking any more about that, but that is one area that we are looking at a lot. The other area is non-continuous flooding, or some form of AWD, mid-season drain. And the question really becomes in this system, and I think for all systems, when do you dry these fields? When is it appropriate to dry a field? In California, it's very difficult to achieve an AWD system where you have multiple drains. In the early part of the season, a lot of the water management is dictated by your weed control, the herbicides that go on, and controlling nitrogen. So for the weeds, in California, when you apply a herbicide, you are not allowed to have that water leaving the field. The field has to hold the water for a certain number of days. It might be a week, it might be a month that the water has to be held. For nitrogen, we're applying most of our nitrogen pre-plant, and so if you drain it during that early period, you're going to lose a lot of your nitrogen. At booting, we have cold nighttime temperatures, very similar to Australia and probably other parts of Asia, maybe in temperate areas. We actually encourage farmers to raise water during this time to protect the panicle from sterility, from blanking. And then finally, during the grain fill period, we do not want to risk poor grain quality. Again, it takes a long time to get water on and off these fields. If it gets too dry, our grain quality will suffer. So getting back to nitrogen management and where that fits in, because we want to keep N2O low. I've discussed the top part of that already, but just down here at the bottom, in our systems in California, in these water-seeded systems, that nitrogen fertilizer is all taken up by about 40 days. You can kind of see that in this graph off to the right. But the point is about 40 days, that mineral nitrogen is very low, and it would be safe then to introduce an aerobic period. So dry down events, we suggest, should not begin any earlier than 35 days, ideally 40 to 45 days. I'm not going to talk a lot about it, but in all of our studies, we've kept our N2O emissions typically around 0 to 1% of GWP. There have been a couple cases where they've been up to about 6% of GWP by following these kind of guidelines where we know we're draining where mineral N is low. So very quickly, we have a window of opportunity between 35 and 55 days after planting where we could put in a drainage event. This works well with farmers for herbicide applications. Again, the nitrogen's been taken up, and farmers who typically apply a top dress nitrogen can apply it right before reflooding. So we've done a lot of work on this. Mid-season drain, and I know I'm speaking to an audience here where mid-season drains are very common, especially here in Japan, in China. It's not in California. What we've done, and I've just pulled out one photograph here, graph, and we've looked at high severity and low severity. If you look at the typical pattern across the top here, that's continuously flooded. If we have a low severe drain, in this case 5 days where the fields were drained, we see that emissions drop, but then they start to rise as soon as you reflood. If we go to a 12-day drain, in this case, more severe, those drains, when you reflood, you don't see any increase in methane emissions. So we were able to get, on average across a lot of studies, low severity drains were about a 40% reduction. Where we had a high severity, we were seeing about a 60% reduction, simply because of the fact that you're not increasing after that. This is just a simplified picture of what I've just shown you. The left side being typical methane emissions during a season. By introducing drain, you drop those emissions, and then they arise very quickly after flooding in a less severe dry down, but more severe, you're able to keep it low. So what does what do these drains and how do they affect heavy metal uptake? This is a separate study. And it's looking at single drains, not a mid-season drain, and it's looking at, but it is looking at low and high severity drainage events. We looked at safe AWD, where the soils got to be 0 to 10 kPa, medium severity, about 70 kPa, and high severity minus 154 kPa. What we saw is the low severity, that's this group here. We did these drains at PI, booting, and heading. The low had no effect. This is the control here, the continuously flooded, no effect on either total or inorganic arsenic reduction. When we went to the medium or high severity, what we saw was the greatest reduction during booting. And I recall that this is the time when you don't, if you have a lot of cadmium in your soil, this is also the time when you would be increasing cadmium. You do not want to drain your field at booting if cadmium is a problem, but for arsenic, that was the time of greatest reduction. In all, we saw a 40 to 60% reduction in total and inorganic, and again, we're able to really reduce the organic fractions of arsenic. We were able to reduce those by 70 to 80%. So just as a summary of what we've kind of been, these practices are going to be started to be adopted in California this next coming year. There's a program, USDA Climate Smart program, that is pushing out some of these programs for farmers to use this upcoming year. Growers are very excited about it. And in general, what we've seen is a 40 to 80% reduction in methane, almost no N2O. This is very similar to what you'd see with multiple wetting and drying events. We've seen arsenic reductions of 20 to 60% reduction in total arsenic. I have not included the inorganic arsenic in here because some of the studies don't have inorganic arsenic. Cadmium, when we do these earlier drains, we've not seen a difference in cadmium. That may be because we're starting before the reproductive phase, and it may be keeping our cadmium fairly low. Yields, we've not seen a positive or negative effect. I started this work hearing results from Japan, hearing results from China that mid-season drains increase yield. We have not seen that, but we've not seen negative ones at all either. Certainly increasing yields would lead to sort of a win-win-win scenario where farmers would have an immediate incentive to adopt those the practices. So I want to close up with just a couple thoughts on yields, and then I'm going to finish it up with a couple thoughts on where we can practice these mid-season drains. I worked a lot with farmers, and practices that reduce yields are not very attractive to farmers. It's going to be very hard to get them to adopt a practice if there's any kind of yield reduction. Many studies, not all, but many find that AWD typically reduces yields. And I think we're going to see in this talk here, there's going to be somewhere that actually increases, and that's good. But in those studies where yields are reduced, I think a lot of times we assume that it's water stress. You look at papers when they're written, and the assumption is, the default assumption is that somehow there's a drought, water stress that's causing a reduction in yields. And certainly in some cases that may be. However, there's a long list of other possibilities that I think we as agronomists need to consider. If we're going to try to raise yields, we need to know what's causing any kind of yield reduction. Certainly disease is a big problem. When you start to drain fields, diseases can become a problem. Blast, brown spot are two that come to mind. Certainly in the US, where there's blast in the southern US. In California, we don't have a lot of blast, but in the southern US, blast is a big problem. Where they're doing these non-continuous flooding practices, and they've been adopted quite widely, they have to use blast-resistant varieties. Otherwise, the yields are going to be very low. Weeds can be a particular problem, especially early in the season. If you're draining early in the season, that first month, you're going to really promote weeds, and that can reduce yield. And I think the last one, nitrogen loss, is very important, especially where you're doing a lot of AWD, a lot of drains and refloods. You're promoting nitrification, denitrification losses. And we've already talked about how that increases N2O, but it's going to lower your nitrogen use efficiency, your nitrogen uptake, and hence your yield. So those things we really need to look carefully at. If we optimize those, maybe our yields would become a little higher. So I want to close on this last topic, and it's recognizing that precision water management is a powerful tool, as we've talked about, but it's not always possible. And if we looked at irrigated or rain-fed fields, there's a lot of cases where rain-fed fields, farmers are not going to drain their fields due to risk of drought. They might not even be able to drain their fields. In climate, dry season versus wet season. In a wet season, in many cases, it may not be possible to drain. Certainly in the dry season, a lot more opportunities to put into practice some of these things. Irrigation infrastructure is something that's very important to consider. Do farmers have access, and are they able to turn on water to their fields when they need it? Are fields hydrologically connected? Some irrigation schemes, all the farmers are on the same irrigation, they get water at the same time, they're all connected. So if one farmer wanted to do an AWD, he couldn't because all the farmers around him are flooded. Need to recognize these things. Topography, this is just a field somewhere in Southeast Asia, and you can see there's a slope. During the wet season, probably the bottom areas of those fields are going to stay flooded the whole season. In the top areas of those fields, it may be dry for a lot of the season, or at least unflooded for a lot of the season. So there's a lot of limitations that we need to recognize as we try to promote these. I wanted to just get an estimate of how much land we could do that may be suitable for non-continuous flooding practices. And this is very rough. But a lot of you know Ole Sanders. He published a paper in 2017 with a group of co-authors looking at the climatic suitability for alternate wetting and drying in the Philippines. The climatic suitability does not account for irrigation infrastructure, landscape position, or anything else. It only looks at rainfall and soil properties, the amount of percolation in a soil. What they found was 90% of dry season rice was suitable for AWD. Only a third of the wet season rice was suitable for AWD. And then I went to McLean et al. It's hard to get this data looking at different rice ecosystems across Asia, and I'm sure, this is from 2002, I'm sure it's changed. But they've identified 5 different systems here: upland, deep water, rain-fed, irrigated wet season, irrigated dry season. About a third of it is irrigated dry season, a third is rain-fed. Again, those numbers have probably changed over the last 2 decades, but this is just somewhat of a mathematical exercise. Going back to Ole's and using those assumptions and applying those assumptions from Philippines across all of Asia. I realize there's huge problems with that. But if we recognize that in uplands, methane's not a problem. Deep water rice, you're not going to be draining deep water rice. In rain-fed systems, you're not going to be managing water, but there is going to be some unintentional AWD that can be managed, particularly with nitrogen. We really have these 2 systems, the irrigated wet and dry, and if we apply Ole's, the Sanders math and assume all of Asia is like the Philippines, about 40% of Asia land is climatically suitable for AWD. So the number isn't important, 40%, that's not very important. The fact is that a lot of land, there's a lot of rice area in Asia that is not suitable for alternate wetting and drying. And so I think there we need to really think about what are other strategies that we can use to address those sorts of situations. So my closing slide. Through water management, we have incredible potential to mitigate both greenhouse gases and heavy metal uptake. It's a powerful tool, this water management, but and win-wins are possible, certainly, but we need to understand the metals that are actually in the soil. We need to understand the problem we're dealing with. And then we need to understand the particular rice systems and the recommendation domains for these practices. And in cases where that's not possible, and I'm guessing it's quite a bit of area in Asia, other solutions need to be explored. So with that, I'd like to thank you for your time.
Thank you, Prof. Linquist, for your very interesting talk. And then before going to, we still have a time for a question, and then before going to this session, a quick question answer. I need to apologize to you. I forgot to introduce my co-chair. This is Mrs. Jennifer from FFTC, and she's in charge of online. And then we are two to take this session. So again, we still have a time. So if you have some questions, yes, first we take some questions from the floor, and then later we also take some questions from online if possible. So yes, I see one hand from right side, and then I hope you have a microphone. Yeah, please proceed to the microphone, and then yeah, microphone is standing there.
Thank you, Dr. Bruce, for your nice presentation. I have one small query, that in grain concentration of some elements, some heavy metals, that is increasing on draining event. However, for some elements, some heavy metals, particularly this cadmium, nickel, chromium, this concentration is increasing. So what is the chemistry behind that, maybe in soils, what is happening, or what is the plant physiology that is just increasing the concentration of these heavy metals?
I think I understood your question. You're asking about the mechanism for uptake of other metals?
Yeah, particularly the cadmium, chromium, nickel. The concentration of these heavy metals in grain is increasing on draining event.
Yes.
So what is the mechanism or chemistry in soil that is increasing the concentration ultimately the grains?
Yes. I'm going to be honest with you. I am not a soil biogeochemist. And I have looked at some of this, and it's going to vary for each one of those species. Sometimes it's a shift of speciation, and sometimes some of them interact more with iron. But I'm not going to be able to talk specifically about the increases for each one of those specific metals.
Okay. Thank you.
I am sorry about that.
Yes, please. Microphone is front.
Just open. Okay. Thank you for Dr. Linquist for your very excellent and informative speech, and it integrated multidiscipline knowledges. So that make me to can rethink about the strategy or measures to control the heavy metals and GHG emissions from paddy rice. I come from Taiwan Agricultural Research Institute, and the most important things that I am very interested in is that because we can integrate multidiscipline knowledges to plan the strategy for maybe for specific farmland. And I want to know if such measures has been promoted broadly in the world, and how we should to teach the farmer follow such measurements, or how to precise control maybe the water, the soil moisture, or how to control the water levels in the field. Thank you.
Okay, I think I understood your question. You talked about a lot about the multidisciplinary, all of that. I would say, I mentioned the fact that there's a lot of disciplines that are important in understanding what's going on. Some of it involves a lot of very basic science. We're not expecting those people to be talking to farmers. It's groups like this that I think are really important. It's pulling in that basic science and then seeing how it works in a field, and taking those field measurements, and then taking what we learn as more applied scientists, then taking that to the farmer. I don't expect a lot of that basic science to work its way easily down to farmers, but it's us, I think, in this room, largely, that are responsible for kind of taking that basic knowledge, putting it into applied fields, and then disseminating that information.
Okay, thank you.
Did that answer your question?
Yes, thank you very much.
So, thank you.
Hey, sorry. There are two before you. So please go ahead.
Thank you very much, Mr. Linquist, for your nice presentation. Actually, you detailed out the two stories together, and it was an excellent presentation I have ever heard, combining these two stories together. Actually, I have two little questions. Like, as you mentioned that due to nitrification, that nitrous oxide emission increases when we dry up the soil.
Yeah.
and that reduces the nitrogen use efficiency. Yes. But the thing is, when we dry up the soil, the ammonia volatilization also drops down. So did you ever tried calculating these two issues together to calculate out how much nitrogen use efficiency been getting when we dry up the soil or something?
Certainly in California, all of our fertilizers are buried. So ammonia volatilization is not a problem.
Okay.
I would have thought that potentially here, I think with AWD, I'm not sure of all the practices that are being, especially with fertilizer application, what are the recommendations for fertilizer applications when you're doing these multiple drying events? I could see situations where ammonia volatilization would be made worse. For sure. And I could see potentially where it could be improved on. So I think
that is the situation in Bangladesh. What we do, we just surface apply the prilled urea, so that volatilizes a lot.
Yes.
And
I think that would be that generally you would see not only nitrification, but you would see a lot of volatilization losses as well. So when you start to implement these, it's really important. Again, it gets back to yield. It gets back to economics for a farmer. You're starting to pay more for fertilizer now. Optimizing how we apply those fertilizers is very important for a number of different reasons, as you mentioned. It's a real challenge for us.
Okay, thank you very much.
Thanks so much. So, yeah, we have 2 questions before we close, and then please make your question shorter so that we can accommodate one more question.
Thank you very much for interesting speech presentation. So I have one question regarding the AWD in Philippines regarding through your presentation. So you said that 40% of puddle field in Philippines is suitable for AWD. It means that most land is not suitable for AWD. But I let the Philippine government to promote AWD for saving water as a policy. So what do you think about the disturbing factors in AWD promoting in Philippines or Southeast Asia?
Oh yeah, it wasn't 40%. 40% was a number I'd gotten for all of Asia. But I think the point, they were looking just at being able to practice AWD in a field, the ability to manage water in a suitable way to reduce greenhouse gas emissions. And in the dry season, because it is dry, it's very easy to do that. In the wet season, you have very little water control. You have rain events, and then it depends a lot on your soils. A lot of them are very heavy soils. There's not a lot of percolation, so your soils your water tends to get very high in the thing. Now, I'm not sure in the Philippines. I'm not familiar with the Philippines. If water savings during the growing season or during the wet season is very important or not, but certainly in the dry season, maybe it is important. And it's during the dry season where you actually have a lot more control and ability to reduce water use because you have that control over your water.
Okay, thank you very much.
That answer your question?
Thank you so much.
Okay, so last question, so Dr. Susan-chan.
So this is Susan Chan from FFTC. Thank you very much for your very informative presentation. One question is for seeking clarification. So you mentioned the mid-season drainage. You have 40 to maybe 60% or 75% reduction in methane.
Yep.
Is that only calculate that part of time or the entire growing season, the reduction? When you compare it just that during that time, the reduction between the flooded and the drainage, or the entire growing season?
It's for the entire growing season.
Oh, compare. So that part already have significant.
Yeah, so the challenge then becomes we're able, with a mid-season drain, and I was talking to Kaz yesterday, I think we're able to control the last half of the growing season emissions. It's going to be, the challenge is that first half. And how much emissions are we getting that first half? Those are much harder to control than the second half. But yes, when I'm talking about a 40 to 80% reduction, it was in that, it's considering the whole seasonal emissions we're able to reduce by 40 to 80% with a mid-season drain.
Oh, I thought that in the beginning, because when you start flooded, there's some free organic matter in the soil.
Yes.
So, I mean, the methane production maybe it's more significant in the beginning, but that doesn't count because later on when the plant grows, there are also some plant exudate.
Yeah, usually people consider that the first half of growing season emissions are really due a lot to the previous residues, maybe roots from the previous crop. The latter half of the season is often attributed largely, not completely, but largely to maybe root exudates from the plant. It's a lot more plant-driven, that last half.
Okay, sorry, allow the second one. I think that the one that I noticed is that there are different reactions to the AWD, and I think it's all related to what time you initiate the AWD. So in your study, it's started from 30 to 55 days after. So it's already past the booting stage. And then you also pointed out maybe water stress, maybe the yield reduction, maybe due to water stress or nitrogen. And I think nitrogen would play a very key role here. And so this is just as food for thought. So I hope that today's discussion, when speaker talk about the AWD practices, please specify when did you start to do this AWD. I think that would have different results.
It will.
Yeah, thank you. Sorry.
Thank you so much, and then time is up. Sorry for those who wanted to make a question, but we have a coffee break, and please approach him and then give your questions and make a discussion. And then one person online, but he's one of the panelists, so please hold your questions and then show your questions during panel discussion. So once again, thanks, Prof. Linquist, and please give him a round of applause.
Okay, once again, thank you very much for the keynote speech, Dr. Linquist, and also the moderator, Dr. Hayashi and Mrs. Jennifer. Now we are going to have 15 minutes break time. Coffee and tea will be prepared outside the conference room. Please come back to your seat by 11:30. Thank you.